I would like to call this meeting to order. I would like to call this meeting to order a pepperoni pizza. Big one. Anyway. So, by way of announcements, I understand that the grades for test 1 went live just a short time ago, so cue people groaning about 15-30 seconds after I say that. Just kidding. Actually, the marks on test 1 weren't too bad. I believe the average was an 80-something, right? Yeah, like 80.2 or something. Yeah. So not too bad, not too bad. All things being equal. So, on Monday, we had our lecture remotely via live stream. So, for any of you who are following along online, it was a live stream, not a recorded lecture. So there you go. We polished off our topic about floating point numerical computations, and we had just gotten into testing and exceptions. This is going to be a short unit. So, in fact, we need to keep motoring because time grows short. So. Thank you. So, one of the key things that we went over last time was the difference between Whitebox and Blackbox testing techniques, or program verification techniques, more broadly. I always think that white and black box are kind of misnomers. What is actually meant by those is transparent and opaque box testing. With white box testing, generally speaking, you rely on knowing program source code in order to generate your tests. You can see what's going on and formulate your tests accordingly. With black box testing, you are interested only in that which goes in and that which comes out. And just a reminder of our well-versed software design principles, modularity and decomposition is the property of having your program so composed that many of them could be stuck together, one could be swapped for another. This is aided by a view of software that is centered on input and output. So you want to take a large problem, break it into tiny little pieces that are easy to solve, and then by the composition of those, put together a larger program. Small programs are much easier to work with and deal with than large programs. When a program becomes large enough, it is virtually impossible to do anything with it anymore. So, one of the primary ways that we, as computer scientists and people who write software, one of the best weapons we have against the creeping complexity of our programs is the decomposition of that program into smaller and smaller pieces, or at least sufficiently small pieces that the problems can be addressed at that level. Being able to do this means the difference between being someone who can be employed writing software and someone who can't. So, the other big word in software design is abstraction. So, what abstraction allows us to do is ignore those details of an implementation which are irrelevant, right? We can deal with a function without having to know how it performs its operations. All we need to know is what goes in and what goes out, right? So abstraction, also a very important principle. Black box techniques feed into these design principles quite heavily, since a black box perspective on software is a modularized view of software, and it views the piece of software as an abstract entity, right? It views it as a non-interpreted entity, right? Okay. Any questions so far? Good. So, modularity enables better black box testing. So not only is black box testing good for modularity, but modularity is good for black box testing. When we develop test cases for every function within a larger program, this is known as unit testing. So the testing of the individual modules of code, this is known as unit testing. Testing the program to see if all of the modules have been hooked up together correctly and are all working in tandem, this is known as integration testing. So, it's not sufficient to have each one of your modules behaving in the manner you expect it to. You also must use all of those modules in such a manner that you do not, for example, violate the implicit conditions on those modules and other associated facts. So, good. Regression testing is where you have a bug, right? You fix that bug, but you hold on to the test case that revealed that bug so that you can test to see if that bug reemerges later. Bugs can be tricky things. They sort of have this property of a bug will be able to hide behind other bugs. Normally, it's only possible to see a few of the major bugs in a program at once. So, if you fix one, you might be in a position where 3 more appear before your vision, and then you have to fix each of those. And each one of those could have 3 bugs behind it, depending on how good a programmer you are. So, when we fix a bug, if we perform regression testing, we should have 2 test cases. We want one test case that fails if the bug is present, and another that passes if the bug is fixed, right? That way you can come at the thing from both angles. You keep both of these test cases around after the bug has been fixed, and this way you can detect if, Joe Schmo, the bad programmer at your company, has, accidentally reverted your repository to the state that it was in September for this one module, and all these bug fixes that have been going on for a couple of months were somehow lost and out of the main branch, and now you have all of these customers coming to you about these bugs that you thought were fixed. It's like, if you perform regression testing, then you pick that up before it gets out to the consumer. So, one topic in testing which has become sort of very highly popular in recent years is the idea of continuous integration testing. This is made more possible by integrating your code project into some kind of supra system, some kind of software system that manages your code, right? So one of the primary examples of this is Git. Who here has heard of GitHub? Fair number of you. How many of you actually have an account? Fewer of you. Everyone in this room should have an account on GitHub. And in fact, if any of you take 1xC3 with me at some point in the future when I'm teaching it again, you will all have GitHub accounts because we use GitHub rather extensively in that course when I'm teaching it. So, so what GitHub does is it's a code repository. When you make changes to the code, it keeps track of what changes were made, when they were made, and by who. It does this all automatically, right? It also allows you to have multiple people working on a project, all working on the same files even, making mutual modifications, and it gives you some kind of a system to work out the problems if two people have made a modification that conflict with each other, right? Yes?
Did you say keeps track of bugs?
It keeps track of what?
Did you say keeps track of bugs?
Well, we're going to get to that. We're going to get to that. So, it can be used for bug tracking and issue tracking as well. It has actually a tab specifically for issue tracking. So, you know, while managing a repository is, you know, a skill unto itself that's kind of separate even from programming, although it's related to programming. This is definitely the kind of skill that anybody who's seriously employed as a software engineer in the year 2022 is going to need. Like, knowing how to manage a code repository, or even like at the level of knowing how to not screw up your colleagues' work in a code repository. This is now assumed knowledge for anyone in the field, right? But anyway, so one of the interesting things that you can do with GitHub is a thing called continuous integration testing. What you can do is you can set GitHub up such that it runs the code that you're feeding it to ensure that certain test cases have been met. So you code up your test cases in a particular manner, right? You set GitHub up such that whenever it pushes code, it compiles that code and runs those test cases and watches the results. And you can even set GitHub up such that it will reject any changes that fail the tests, right? Now, I know that this kind of sounds, okay, sure, you know, this doesn't necessarily sound like a big deal. It's a big deal because it can be done all automatically, where this formerly was the job of, you know, entire departments of quality assurance, right? This is kind of this is the direction that things go, particularly in software development. Things that used to be a person's whole career will, you know, gradually over time become more and more automated so that you need fewer and fewer people in that position over time. So once upon a time, and you know, there are still many people with this profession actually out in the workforce, you would have testing engineers. All they would do is test software. And they were very good at it. Like, that was a job, that was a thing you could go into, was just testing, right? Like, testing as a career path. A lot of the busy work has been sort of extracted out of it over time. Back in the 90s when we didn't have these types of tools, you tested less well, and you know, you had to hire more people to do it. Now, one person goes a lot further if they know how to use tools such as continuous integration testing. So, you know, if you want your company to be competitive in the software marketplace, you must take advantage of recent developments in technology. Any questions about that? Cool. GitHub is actually really cool. Anybody have any independent software projects, like just kind of like hobby projects that you've started or tried? A little bit? You guys using repositories for it? Yeah? No? You should try it. It's so good. It's so awesome. Great. So, here is an example of what GitHub looks like. I won't dwell on this too much because, like, you know, well, for one thing, the interface has changed a little bit since this, but, you know, you can have tests run automatically on the code that you push to a repository. Because, like, it kind of gets back again to this problem of the principle of least privilege, right? You don't want to trust things any further than you have to. And that extends not only to software, but also to people. If you're like running a software company with like 5,000 people, and like you can't personally vet everybody who gets hired, right? Or, you know, if you can at 5,000, just expand that company until that's no longer possible, right? So, like, what are you going to do? You're going to let this, like, you know, this straight out of high school kid off the street have access to all your most, you know, precious and important programming, you know? What if they're a spy from a rival company, you know? So, restricting privilege is a very important thing. And this is kind of a form of restricting privilege. So we've talked a lot about what different types of test cases are, without yet providing much guidance on how to actually write them. So this is a slide on how to actually write test cases that might be useful. So exhaustive testing is impossible for reasons I've explained before because of the state explosion problem. However, that does not mean that you can't exhaustively test all representative test cases, right? So basically, there are a few things that you really want to ensure for your software when you're testing. Number one, all different types of valid input should be tested, right? If your function can accept a string, a tuple, or a list, and you only test strings and tuples, you have not completely tested that program, right? You also need to take into account what are called edge cases. An edge case, it's a number where things change from one state to another, right? So a very common example of an edge case with a loop, consider loops for an instance. Does your program still behave correctly if that loop does not even execute, right? In the case of a for loop, what does this thing do with an empty data structure, right? In the case of a while loop, what do you do if the while loop's loop condition is initially false, in which case the loop doesn't execute? Does your program still work, right? So these types of edge cases, would that be Blackbox or Whitebox testing, the finding those types of things? Anybody? Yeah?
Whitebox?
That would be Whitebox testing. In order to know what the particular edge case is for X loop inside of Y function, you need to have actually taken a look at the condition and see what the condition is, right? So far as it goes. So you also want to test all the different types of, like, for example, numbers that you can have. You know, does this work with positive numbers? Does it work with negative numbers? Does it work with zero? Does it work with composite numbers? Does it work with odds, evens, primes? How, like, test numbers, right? The more test cases, the more assurance you have that your program is correct, at least if it passes those. For data structures, a bit one is the empty data structure, as I've already mentioned. A data structure containing only one element is another good edge case. These, incidentally, there is a term for them, singleton data structures. You might hear me occasionally refer to a singleton string or a singleton list. That's just a list that contains only one thing. And if you're testing for subsequences, give a test case where the thing that needs to be found is at the beginning and at the end of the data structure. This is actually a very important one. This one will reveal quote-unquote off-by-one errors, which are very common when you're addressing the indexes of things like tuples and lists. Basically, if you're doing, for example, a search algorithm, and you put the thing that it's supposed to return in the very last position, and your program fails to find it, then you know that that's obviously a bug, right? And it's easy to have that situation arise if you've messed up calculating the indices. Does that make sense? Good. So let's return to our max product. Boom, this guy, right? Calculates the maximum product of the maximum 12 adjacent integers inside of some string of integers. So, the types of end cases that we would develop for the max product algorithm. We know that we want 12 adjacent integers. So let's try an input string that is the minimum possible length. In fact, we would also possibly want to test the behavior for lengths less than this to make sure that the program doesn't throw up, that it doesn't puke its guts all over your motherboard. Check for a minimal output. Minimum possible output is 0, so we should check that. Maximum possible output is 9 to the power of 12. So 9 times 9 times 9 times 9, etc. We should try that one as well. Incidentally, do you cram all of these into one test case? No, you absolutely do not. How do you know which one of these conditions failed if you're testing all of them at once? It's impossible. Test one thing at a time. Scientific method. Isolate your freaking variables. So, again, we also want to test to see if the substring is at the beginning or at the end of the data set, right? We want to test that off by one condition. So, let's consider the max product of 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. The maximum product will be these last 12 digits, right? Because these ones are smaller than those ones, right? You could make this even more explicit if you wanted by, like, you know, making the intended range that you're going to capture all 9s and then the other ones as 1s or 0s. You can do that as well, and I guess that technically also tests the max output, but you know what I mean. So when we test this, we get 121,927,680. It turns out that the actual value, if you verify this with a calculator, is 182,891,520. So we have a mismatch. We have a failed test. A failed test is always a glorious thing because that means that you know where the bug is. You know? It's better to have a test that fails and know where the bug is than have no tests fail and still have the bug. That just means you're not very good at writing tests. So, it is not always possible to have an independent method of verifying these things. In this case, it's easy because we can just plunk it into any standard calculator and bing, bang, boom, Bob's your uncle. A lot of computations will be sufficiently complicated that you either have to set the test case up with the output you want in mind and sort of back calculate the inputs from the output you want, which is possible, or sometimes you can find an alternative algorithm or an alternative method which you can use, some other method which should calculate the same result. You can use that to verify whether or not you've got your whether you've got whether you've got it correct or not. One might ask, if I already have an algorithm that implements a particular function, why would I not just use it instead of doing my own thing? And the answer to that is, you might be trying to develop, for example, a more efficient version of an algorithm. Or you might have a code base, you might have a program that already works, that you want to add a feature to, right? Doesn't necessarily change what the output is going to be. The older version can be used to check the newer version, particularly in those areas of the code which are not new. And if you don't think that adding a feature can introduce weird bugs in parts of the code that you don't expect, that you haven't been programming software very long. So we find, in the end, this should be an 11. What has essentially happened, if we verify this independently, this is the value of these guys, excluding the 9, right? So the algorithm checked up until it hit the 8, then it said, okay, I'm done. Never checked the 9, never found this larger number, right? So that's quite easily fixed. You just have an off by 1 error here because this is off by 1. And once you change that, everything works fine. Any questions? Good. So, Whitebox techniques rely on knowing the program's source code. So we're going to go through a couple of Whitebox techniques. Code review is a process whereby 2 or more developers visually inspect program code, typically several times. It's a bit like proofreading, right? Generally speaking, it'll be more senior people, more experienced people who are reviewing code, right? They'll be checking for a bunch of things. Basically, they'll be checking to make sure that you've programmed exactly like they would have programmed it. They'll be checking for things like best practices, potential inefficiencies, and common vulnerabilities. Like, for example, best practices. It can even be syntactic stuff. Like, a lot of companies actually have internal, a lot of companies or projects have like rules about what kind of variable names you can use and stuff like that. And it's sometimes stuff, it depends on like the language that they're using. Like one that I've seen a few times is the data type of the variable must be contained in the variable's name. Like, it's like myvar_int, that sort of thing. Because it's very useful to know what the data type of a variable is. And, it's more useful if you know that in situ, right? It's not a bad practice, actually. But like the company, that could be enforced at the level of the company, and somebody reviewing your code could say, look at all these variables. You haven't used the code, you haven't used the naming convention. And it's like, oh, sorry. It's like, well, redo it, sort of thing. Potential inefficiencies. This is kind of like, could I think of any way this code could be optimized type territory. And we've talked a fair amount about, code optimization. This probably has the potential for the most nerdy arguments of the three of these. And common vulnerabilities are another one. Sometimes, if you do a particular thing in a particular programming language, you open yourself up to hackers. A good example of this that we're going to be covering in this class later on, anybody in this room heard of SQL databases? Anybody know what SQL injection is? So, yeah. So there's a type of hack, which is actually one of the most common forms of hacking that exists and is currently practiced today, called the SQL injection attack. Basically, SQL is a database querying language. So you write out queries for the database, and they look a lot like code. And they behave like code. And it is possible, if you don't sanitize your inputs, it's possible to do things like sneak special characters in, which call for operations inside of an SQL statement that the person who set the system up never intended. So, like, for example, well, we'll have examples when we do the unit on SQL, but yeah, you can get at passwords, right? Like, login credentials are very often kept in SQL databases, right? SQL is vulnerable to SQL injection attacks if you use certain bad practices. So if somebody can catch you from using that before it gets shipped, you might save your company millions upon millions of dollars and several lawsuits. So, yes. Code review tools can also help the process. So, one thing that, one type of testing is coverage testing, right? When you write a program and you are testing that program, one thing that you want to make sure happens is that every single line of code inside of that program gets executed at least once, right? So it turns out that there are software tools which can be used to analyze your program during execution to see whether or not every statement in the whole line, every statement in the whole program is actually being executed or not. This is known as coverage testing. For C/C++, the tool is called gcov, and again, that's something we talk about in 1xc3 when I teach it. There are formal code review methodologies, which we're not going to get into, but depending on where it's being used, code must be subjected to increasing levels of scrutiny. Like, it is not correct for the amount of code that went into, like, one of my son's little toys, Fisher-Price toys. It's not appropriate for that to be to have the same level of review as a nuclear power plant, right? Nuclear power plants, if it blows up, that can be a big problem, So they're subject to a very strict amount of review, right? And there are formal methodologies for going about doing this. But, again, a nuclear power plant is not going to be testing your code on the basis of Blackbox functionality, right? They need to know how the code is happening, right? So, code coverage. I kind of already touched on this. Do the test cases exercise all lines of source code? So, for example, if we have if statements, does every branch of the if statement get executed? If we have loops, does every loop actually loop? We also have static analysis. Static analysis is actually a very broad term. Basically, static analysis is any analysis you do of a program without actually running it. Anything that requires the running of the program is known as dynamic analysis. Static in stasis, dynamic while moving. So we can run automated tools to find flaws in programs. Like, for example, am I using a variable where it doesn't exist? Am I trying to access past the ends of a list or an array or something like that? A lot of this is more relevant to C because a lot of more modern programming languages build in a lot of these types of safety features into this type system. But there's plenty enough development that still goes on in C and C++ that such tools are necessary. The one for C and C++ is called CPP check. And it just goes through your code and identifies common problems and gives you a report. So, good. Any questions about any of that before we move on to the process of debugging? Good. So, we've talked a lot about testing. Now what do we do if we encounter a failed test case? Once your testing has shown that your program doesn't behave as intended, you have to identify the bug and then fix it. To find the bug, you need, number one, a test case that reliably fails, and number two, you need some way of understanding the internal state of the algorithm, right? So the key word in this sentence is reliably. Very often you'll see bugs that are particularly like community contributed bugs for community driven projects where it's like, here is a bug, and then the developer is like, could not replicate. It's like, it's not exactly saying, I don't believe your bug exists. What it is it's saying, I can't reproduce this bug, so I can't fix it, right? It's kind of like a sly little, it might be your problem, but yeah. So, what methods do we have to understand the internal state of a program? Anybody? Everybody? Oh, yes.
You can print at different steps, especially
Using print statements at various steps, especially where the error might be present. Yes, absolutely. That should be the programmer's first line of defense. How else can you see the internal state of your program?
Python tutor?
Python tutor, yes. And I would extend to that the class of programs which perform similar operations. We will generally refer to them as debugging environments. So, to understand the internal state of the program, you can use print statements. This is also known as tracing the program. And you can also use a debugger to step through the program. So, a debugger, and most languages will have a debugger attached to them. It's like one of the first things you make for any language when it comes out, Debuggers integrate into an editor in which you can visually inspect the code. Inside of the debugging environment, you can step through lines of code one at a time, watch their effect on the state of the program, and derive from that conclusions about whether that is correct. Right? You can test it at the level of the execution of individual statements. So this can get tedious though in a program of 10,000 lines of code, where each one of those lines of code is executed 1,000 times, how do you pick out any particular point in the execution of a program by stepping through them one at a time? Very difficult. You use breakpoints for that. Generally speaking, if you double click on the line number to the, like this is kind of the standard format for it. If you click on the line number for a particular line in code, the debugger can be run to that point, at which point it stops. You can inspect the state of the program, and you can like step forwards, or with the really fancy ones, you can also step backwards from that point, right? And it'll stop there every time it hits that point, right? So if your program returns to it later, you can still see it. Make sense? So in Python, you have idle. You can run idle for Anaconda users if you search up idle, or if you open up the Anaconda launch pad, you'll probably have idle in there somewhere. But it's built into all Python installations, so you have it, you just have to find out where it is and how to use it. But yeah, the debugger is integrated into idle. So in idle, you'll have three things: the code itself, a shell in which to run code, and the debugging control, right? Inside of the debugging control, you can view your local variables. You can see you have go, step, over, quit, etc., etc. You can view which variables you see. This is actually a kind of a minimal debugger in comparison to a lot of them. Yes?
Is there one in Jupyter?
I think, did we take out the Jupyter Superpowers notebook? Yeah. There is one. We'll see about having it put back in, right? Yeah. We'll talk to Mark about it. Yeah. Yeah. Like you can. There's a lot of stuff you can do with the Jupyter environment actually, which might have been useful during the test. But yeah, so I just wanted to talk a little bit about Python Tutor since we've been using it so much over the course of the semester. So it takes a slightly different approach to this. It iterates out all of that data for every single execution of a single statement in your code. Then it puts all of it into a timeline at the bottom where you can pull that slider along, right? You can actually, so their equivalent of breakpoints is actually, if you click on a line of code inside of it, it'll like highlight it in red, and then it will, anywhere that line of code gets executed, it'll put a little red tick mark on the timeline so you can, find them on the timeline. So that's how it solves that problem. Frankly, I think that Python Tutor has one of the best variable views that I've seen, because it actually groups things by function and shows you the stack frames and stuff. Good. Any questions? Right. So let's talk about exceptions. So, let's think about programming. This is kind of a drastic shift in tone. So, let's say you had a function which is supposed to calculate the maximum of something. What do we do in cases where it gets invalid input? Right? What should it return? Physically, what should it return? 0? Well, question? No, answer?
I was just going to say an error.
An error, yes. errors go by a lot of names in programming. In Python, we call them exceptions. But yeah, in like Java, they're called runtime errors. Yeah, but yeah, we're talking about raising an exception, obviously. Let me motivate it though. If you put 0 in there, that's not a good one because like the maximum, if you're going for the least large thing as the default value for the output of a maximum, then that's not 0, it's like the maximum negative number, and like technically speaking, Python doesn't have a maximum negative integer. So, nope. Like you can think of the list -3, -2, 0, -1, the maximum, the correct maximum of that is 0. Infinity? No. Some programming languages have a not a number value, which is kind of like, that's closer, but that still might be valid in some cases. False? This is kind of what we've been doing so far, is just returning false. But it turns out that false isn't a great thing to return either. If you examine things from the level of individual bits, false is actually has the same bit representation as 0. So, let me just so false equals 0 is true, right? Because false and 0 have the same underlying bit representation, and that is what equality is testing. So, false isn't a great thing to use for this purpose either, despite the fact that that's what we've been using so far in this class for that purpose, right? It also kind of works against the idea of modularity. There we go. So, the idea of a function is that it should not require that much from the program that calls it. What it requires of the program that calls it should be just the relevant inputs, and it should just give the relevant output, so that it can be used cleanly, easily, and efficiently. What happens to this algorithm if both max and min might return false in the case where L is of inappropriate size? How much bigger does this nice simple little function get? Right? You have to start introducing all kinds of if statements and, intermediate assignment perhaps, and all kinds of stuff like that. And who wants to deal with that? Not to mention the obligation to continue returning false once you have received a false. This puts too many obligations on the calling program. It's not good practice, although we have been using it so far. So what does Python itself do? Right? Let's consider a situation. Input, let's say we want a numeric input. Input, give me a number, punk. No. Invalid literal for int. No. Right? Value error. This is an exception. When type conversion fails, you get a value error. Right? We're going to learn how to handle these. Exceptions allow Python to deal with situations where it tries to execute a statement that isn't well defined or violates some condition. you can actually create your own exceptions using the key, you can, excuse me, I was about to say something slightly inaccurate. You can call your own exceptions. You can create an exception occurrence using the raise keyword, like raise value error. You can create your own value errors. Raise value error. There you go. You can even give it a description. Right? So once an exception event has been detected by the system, it essentially dumps everything that it has unless that exception is handled, right? So we now recognize a distinction between handled and unhandled exceptions. When the exception is handled, something other than the program crashing happens. When the exception is unhandled, the program crashes. Pretty much all of the exceptions that you will have seen so far have been unhandled. And that's about as much time as we've got for today. Thank you very much for your time and attention, folks. We will resume the class on Friday. Is it Friday? Yeah, it's Friday.